let's look at the discrete time Fourier transform properties. These are listed on the handout. Some of these, I'll only go over a few. You should be familiar with these from other transforms we worked with. Hopefully this is all getting a little tedious at this point. But this is the notation we'll use for the delay property. The discrete time Fourier transform of the delayed sequence is just the transform of the undelayed sequence times e to the minus j k omega. This term has magnitude 1, this exponential, so this just changes the phase spectrum. There's no change in the corresponding amplitude spectrum. The frequency shifting or modulation property, if we multiply a sequence by the complex sequence e to the j omega c n, so now we do have a complex sequence that corresponds to a shift of the spectrum of x of n out to the right by omega c, the frequency of this complex exponential. Of course, from this you can derive, using Euler's formula, that when we multiply a sequence by a cosine, then Fourier transform is 1/2 x minus omega c plus x omega plus omega c. We'll have the original shifted sequence, the original spectrum shifted to the right by omega c, and then added to that the spectrum shifted to the left by omega c. The multiplication property, if we have two sequences, x1 of n times x2 of n, then the corresponding transform is 1 over 2 pi, the integral over any 2 pi interval of the transform of x1 and then x2 omega minus u, and here's our old friend the convolution integral, except it's a little different because we're not integrating from minus infinity to infinity, but both these functions are periodic, so we end up integrating over just a period. Of course, maybe the most important result is what's the transform of the convolution of two sequences. Of course, this is important to us because we calculate the output of a discrete time sequence by convolving the input with the impulse response. But as you might guess, I would hope that the discrete time Fourier transform of the convolution of two sequences is equal to the product of the discrete time Fourier transforms of the individual sequences. And then the last property that I'll write down here is Parseval's theorem, which says that the energy contained in a sequence can be computed as it's the sum over all infinity of the sample values squared. It can also be computed in the frequency domain by integrating over a 2 pi interval of the magnitude spectrum squared. Next lecture we'll actually look at using the discrete time Fourier transform to do system analysis of discrete time systems.